Hi again, everyone. Thank you for attending this, and also thank you for inviting me to the organizers. So in the previous talks, we have heard several times the term searches or detection, maybe. So my talk, I'm going to explain exactly what we mean with these terms, starting with the term search on this first slide. So we have seen that we have gravitation wave detectors. These gravitation wave detectors give us the strain data, so the gravitational wave data, which is a continuous time series of regular sampling of the space-time deformation. So you can index, for example, this vector of data with I for the time sample and with an index J for the detector. So this is a multidimensional data set, which is very large. It covers of the order of 1 year of continuous observation. So that corresponds to about 10 to the 11 samples if you consider the sampling rate of about 10 kilohertz. And this corresponds to about 100 gigabytes of data per year. Now, this is not a lot of data, but still in sort of on the scale of big data considerations, but it's still quite a lot of data. 10 to the 11 is not a small amount of data. And doing the kind of science that Frederic showed in her talk, with this data in this form is not really possible. This is because each value of this time sample, time series data set does not actually contain a lot of information about CBCs. In some sense, the information about CBCs is not a lot despite us having 10 to the 11 samples. So the information is essentially diluted across a continuous measurement that takes 1 year, and it's drawn into the noise of the detectors. So what we rather want is not this kind of data. We want a data that looks like this thing, which is a catalog of candidate gravitational wave signals. So basically a list of potential CBC events with some properties each. For example, we want to know how sure we are that a particular candidate is in fact a gravitational wave signal and not the result of detector noise. And so by search, we mean the process which takes us from this data set to this data set. And concretely, this is essentially a set of decisions, of methods, which are going to be eventually implemented in software and executed on computing systems. And then once we have this catalog, then we can take this much smaller data set and do all the kind of science that we want to do, like astrophysical inference, testing of general relativity, and so forth. To go a little bit further, I need to introduce also the idea of detection of a signal. What do we mean exactly by detecting a signal? So imagine you have an experiment, you have some data from this experiment, a data vector, and imagine that you are in a very simplified situation where you can have only two possible outcomes of this experiment. One outcome is called the null hypothesis, and it means that we run the experiment gave us some data. This data contains only detector noise and no signal. So basically, the physical effect that we designed the detector for is not present in the output of the detector. The other hypothesis is called the alternative hypothesis, or the signal hypothesis, if you want. And is that the data contain noise, which is always present in any kind of physical measurements, and a signal on top of the noise. So the task of detecting a signal means making a decision between these two hypotheses. And to do this, we define a function of the data, which is called the detection statistic, and we compare it to a threshold. And this function is, for example, a real valued function of the data. So it's a function that takes us from an n-dimensional data vector to the real axis. And then we choose a value and we compare it. Now, the decision that we will make in this way will in general not correspond to reality. We can make two types of error. We can make a false alarm, or a type 1 error, which happens when the null hypothesis is true, is physically true, but we fail to reject it. So we make the wrong decision. The other type of error is a type 2 error, or sometimes called a false dismissal, in which the null hypothesis is false. So we have a signal in the data, but our test fails to reject it. And this uncertainty is the result of detector noise. So it's noise that prevents us from being able to always making the correct decision. How we choose this function and how we choose the threshold will determine what is called the receiver operating characteristic of the data analysis, which is a curve that can be represented in this plot. This plot shows the probability of making a false alarm on the x-axis and the probability of detecting a signal on the y-axis. As we change this threshold, we move along a line which is monotonic in this plot. Ideally, we will be here, which will mean that we never make the wrong decision. When there is a signal, we'll always detect it, and when there is no signal, we always reject. We always fail to reject the null hypothesis. This is in general never possible because there is the detector noise, but we can get very close to it in some conditions. The diagonal in this plot is the random decision rule. Basically, you have a detector that is completely useless, or a data analysis method that is completely useless, which always gives you a random decision independently of the physical effect. And of course, we don't want to be in this situation. So how do we design a detection statistic then? This is our first task. We have different possibilities, in fact, many possibilities, and I've sort of grouped them in three main categories. The first one, I call it generic detection statistic, which is useful if you really cannot think about how your detector works. Basically, the problem is so complicated that you don't even know how your signal is going to look like, for example, or maybe it's too computationally expensive to simulate the signal. So you really can't use any prior information on what you're looking for. And in this case, for example, what you could do is you could simply take the absolute value of the maximum measurement, and that would be a perfectly valid detection statistic. Another thing you could do is use a neural network. For example, you could simply take your data, give it to a gigantic residual network, train the network to detect, to classify this data. This is really a classification problem at the end. And this method is appropriate if you have lots of data. So if you have lots of data to train your machine, your neural network, then this is a perfectly valid approach. The approach we actually use for CBCs so far actually is a third one, which is based on a likelihood function. And this is applicable to CBCs because, as Frederic explained, we have very good models, theoretical models of the signal for a CBC. So a model allows us to write a likelihood function, which is the probability of observing a certain data set given a model. Okay, and then under some optimality conditions, you can actually prove that if you use the ratio of the likelihood function for the two hypotheses, for the alternative hypothesis versus the null hypothesis, this is an optimal detection statistic in some sense, which I don't have the time to talk about. So that's very good. We have a mathematical proof that this method is optimal in some ways. So we would like to use it, and we can because we have a model for CBCs. So that's what we will use. We will calculate this maximum likelihood ratio because the likelihood generally depends on a parameter vector for our CBC model, as Frederic explained. So we will have to maximize the likelihood over these parameters and then take the ratio between the two hypotheses. So this is what I will focus on in my presentation. So, okay, we need to write the maximum likelihood ratio. First, we need to talk about a data model. So data model is written like this, can be written like this. And this is not a very familiar notation, probably is my personal preference. But I write the noise contribution as an easy part of the noise, which is essentially the fundamental noises that Francesco talked about, which are described by the PST. Okay, then I like to add a hard noise part, which contains all the data quality problems that Francesco talked about. So glitches, spectral lines, things that is basically excess noise on top of the fundamental physical noise sources. And then you have the superposition of all gravitational wave signals. Okay, potentially this is thousands of signals all present in the data at the same time. And if we take one of them, we can write the response of the detector to that signal in this way, which is probably a bit unnecessary at the moment, but you can think it in this way. So you take the tensor of the gravitational wave and you contract it against a tensor that describes the geometry of the detector. And we have seen previously that this can be written down as a linear combination of the two polarization states with these geometric factors which are called antenna pattern. Okay, very good, but this is too complicated already. So many signals, many noise sources, it's already too complicated to write a likelihood function. So we are going to need to do some simplifications, okay? So I'll describe some of these most important simplifications. The first one is we are going to assume that the signals are separable. And by this, I mean that the duration of a signal, of a CBC signal, is much shorter than the average time between the signals, which is a good approximation at the moment. But John will probably talk about this approximation tomorrow. If we assume this, then we can essentially segment the data into short segments, much shorter than 1 year, and use the hypothesis that I described in my second slide, where we can have only two situations, a null hypothesis where there is only noise, and an alternative hypothesis when there is only one signal plus noise, never more than one signal, 0 or 1. And so we break the analysis problem into a detection part, which is what I'm talking about, and a parameter estimation, which will be covered by Charlie tomorrow. And we never have to deal with the possibility that we have more than one signal in the data. So that becomes very easy. Second important hypothesis, we are going to assume that the noise is locally stationary and Gaussian, which means we are going to pretend that the data quality problems that Francesco talked about do not exist. Now, of course, this is not true, but it is true for short segments of data. So for about 1 minute, you can usually, you can segment your data and you can make this assumption that the noise is well behaved. If the noise is not well behaved, well, we're going to have problems. We will talk about this later. The third simplification is that the signal is much shorter than the rotation period of the Earth, which means that the response of the detector during the signal is constant in time. And so the F plus, F cross factors are constants and can be treated as such, which is a huge simplification. For CBC signals, we are also going to simplify the CBC model a lot. So all those nice physical effects that Frédéric talked about, precession, higher order modes, eccentricity, matter effects, cosmology, we are going to forget about them, pretend they don't exist. And our signal model is going to become simply a scaling factor at the beginning, cosine, phase term, like this. This is a very simple signal model with the frequency that is a monotonic function of time. And if you take the Fourier transform of this, you can do it analytically with some approximations. You find exactly the same form in the frequency domain. A complex factor, exponential, and then a phase term that depends on frequency and the parameters of the system. Very good. So let's look at the full picture again. We have the null hypothesis where the data vector contains only noise, stationary Gaussian noise, well behaved, and the alternative hypothesis where the data contains noise plus a signal of this form. A0, DF, and psi are things that depend only on the merger time of the signal at the detector, phase, an overall phase of the signal, the luminosity distance, the sky location, and the orientation are completely degenerate into a single parameter called the effective distance, df. So we can forget about them and only think about the effective distance. Of course, the two masses and the two spin projections along the orbital angular momentum. This is all we need to model our CBC signal in these approximations. And the signal is always going to look like this. It will never have modulations or very complex features. Okay, remember that our task is to write the maximum likelihood ratio for this simplified model. So let's begin. We go to the frequency domain because Canton. In the frequency domain, the problem looks exactly the same, where we have stationary Gaussian noise described by a multivariate Gaussian like this. And so we can immediately write the likelihood function like this, which is called the Whittle likelihood. So basically, it's when you have a linear superposition of a signal on top of stationary Gaussian noise. Very good. It's just basically a Gaussian. Now we are going to make another assumption. We assume that someone told us the noise power spectral density. I'm not going to say how we can make this assumption, but maybe later we can go back to this. So the only three parameters are the CBC signal parameters. So the maximum likelihood ratio becomes like this. So you maximize the likelihood with the signal over the parameters, masses, spins, time, phase, and so on. And you divide it by the likelihood with only noise, which has no parameters. Simpler if you take the logarithm, and you have this expression with this sort of inner product, which is the noise-weighted inner product between discrete time signals. So it's basically sum of products of the two of the samples divided by the variance of the noise at that particular frequency. Okay, very good. We have to continue a little bit more. We want to maximize these over the parameters of the signal H. We re-express the signal with a global amplitude in front and then a normalized version of the signal. And we can find that we can actually maximize the likelihood ratio analytically over A. And we get this expression for the log likelihood ratio, which is the maximum over the normalized part of the waveform of this quantity 1/2 rho squared, where rho is called the signal to noise ratio. And it is the ratio between the inner product of the data with the template divided by the norm of the template, essentially, which is sometimes called the optimal SNR. This H here, we call it template waveform, and this operation here, we call it matched filter. Why it's called matched filter will be clear in a moment. We can go one step further and also maximize over the global phase. We have already maximized on the amplitude. We can also maximize over the phase analytically, and you simply take two templates shifted by a 90-degree phase rotation, and you take the quadrature sum, and you get the SNR maximized over amplitude and phase. This is what we mean when we say SNR. This is also an SNR. This is also an SNR, but these are maximized over different things. And then we are left with the maximization over time, masses, and spins. And this, unfortunately, we don't have a way to do analytically. We have to do it numerically. This is very expensive. Before talking about what we do next, I want to give some interpretation ideas for this operation. What is this matched filtering signal to noise ratio? What does it mean on an intuitive level? You can interpret it in at least three ways. The first way is as the application of a linear filter to the data. I think Canton told you already about linear filtering. And if you express the operation in this way, you have an integral of the data multiplied by this thing in the frequency domain. This is the application of a transfer function in the frequency domain to some data. This particular filter is the ratio of the template divided by the PST of the noise. And this is called the optimal Wiener filter for a known signal and stationary Gaussian noise. So one way to interpret it is as the optimal linear filter that gives you the best estimate of the amplitude of the signal with a known shape. This is why we call it a matched filter, because it's matched on the signal that you want to detect. Another way is to write it like this. So you have the whitened data here, so data divided by the amplitude spectral density, multiplied by the template, normalized by the amplitude spectral density. And this is a correlation integral. So you can also interpret this as the correlation between the whitened data and the whitened template. And the tutorials tomorrow will show you how these interpretations actually play out in practice. You will literally do this operation in the tutorials. There is also a geometric interpretation where you are basically just taking the inner product of the data in n-dimensional space with a unit vector. So basically what this means is that matched filtering is simply projecting the data in one dimension. So the signal model is basically one direction in the data space. So it's telling you that the noise is basically trying to push you away from this direction. But if you want to detect the signal, you have to forget about these n dimensions and only look in one direction, and you will see if there is a signal or not, which is a very neat interpretation. We need to also talk a little bit about the statistical behavior of the signal to noise ratio. So, okay, you calculate it, you get some number, but what does it mean? If you are in the null hypothesis, so if the data contain only stationary Gaussian noise, then if you imagine repeating the experiment many times, so trying all possible noise realizations in the spirit of the frequentist statistic, you will have this distribution for the SNR, which is a Rayleigh distribution. So you see that the SNR will have actually an average value of about 1. So in the absence of a signal, your SNR is going to have on average about 1. So it's not going to be 0, it's going to be on average 1. Why 1? Because you are maximizing over the amplitude and the phase. And so you can prove that this gives you this distribution. It's not too difficult. It's an interesting exercise. If you have a signal, this distribution will shift away from 0 and will start looking more like this or like this. And the louder the signal is, the more this distribution will be pushed away from 0. And so if you can imagine that if the signal is very, very quiet, so if the average SNR of the signal is much less than 1, then this distribution will be indistinguishable from the distribution associated with the null hypothesis, and it will be impossible to detect the signal. So there will be nothing you can do to detect the signal. It will be completely hidden in the noise. And remember, this is an optimal method in some sense. So if you have a quiet signal, it will just be hopeless. So there is actually a horizon determined by the detector noise beyond which it will be impossible to detect CBC signals. For signals which are closer, they will make this distribution move away and away. So basically, we are done according to the ideas in the first slide. We set a threshold at some SNR, and if the SNR passes beyond this threshold, then we reject the null hypothesis and we have our detection method. Of course, we will make mistakes sometimes, especially if the signal is very quiet. We risk missing it. So sometimes we will fail to reject the null hypothesis, even if we have a signal. And sometimes we will promote a false alert to a detection. And this is unavoidable. Of course, if the signal is very loud, then we can afford to set the threshold higher and reduce the rate of false alarms. This is an example of what the SNR looks like as a function of the merger time of a candidate signal and the total mass of the template. So you see, far from signals, this SNR fluctuates around 1, as I explained. And sometimes you see a peak. And here you have actually one of the BBH mergers that we detected. And you see that this produces a very large peak in this surface, basically. And of course, you have all the other parameters. You have the two masses, the spins, and so it's a multidimensional surface, which is very complex. And if you want to find all the signals, you need to resolve peaks which are 1 millisecond wide in months of data. So you can imagine you need to calculate this matched filtering across months of data with a resolution of 1 millisecond only over time, and a small fraction of mass over mass parameters. So this is a lot of calculations. So how do we do this in practice? We set up what we call a bank of templates. So these are two of the parameters of our search space. For example, mass 1 and mass 2, or time and total mass. We put points in this space according to some criterion, and for each one we have to calculate the SNR. Of course, our true signal will in general never be on top exactly of these points. It will be somewhere else, of course. So we need to be sure that we have at least one point, one template, which is sufficiently close to our signal in order to recover the SNR. And this gives us some algorithms that people have developed to actually place these points. So basically what you need to achieve, you need to have a loss of SNR which is under control, typically no larger than 3%. And if you achieve this, then you have achieved a correct balance between loss of signals and computational cost, of course, because the more points you have, the more operations you are going to have to do. This is an example of actual template banks that we had in LIGO Virgo Kagre. This is for one of the search codes that I will describe later. So we cover masses between 1 solar mass and hundreds of solar mass, and we stop at some point at 500 solar masses because then it doesn't make sense anyway. And this gives us about 1 million templates. So it's a lot of calculations that we need to do. Okay, very nice. Are we done? Absolutely not. We are just starting. Remember that assumption that noise is stationary and Gaussian? Well, Francesco told us that we have data quality problems. So we need to talk about what happens in those data quality problems. Again, this is the expression of the SNR. If you look at it carefully, you have the data here. If you have a large fluctuation in the data, for example, a glitch, you will have the same fluctuation in the SNR. So this means that all the things that I just told you in the previous slides are false in general, in a practical situation. So this nice plot with the distributions is completely false. And if you have a large SNR, it absolutely does not mean that you have an astrophysical CBC signal. So this is a huge problem and one of the major pain points when you work with detections. Fortunately, there is a solution. You can calculate other things that are not the SNR, which are a bit more complicated. For example, this time frequency chi-square, which is essentially the same calculation as the SNR, but performed in frequency subbands. So you calculate the SNR in a small frequency band, in another one, in another one, in another one, and then you compare the distribution of the SNRs with the expectation. So you would expect the SNR to be comparable across all frequencies, essentially. And if this is not the case, then this is probably not a CBC signal. And this gives you a way to reject non-stationary noise. And I can show an example of this. This plot shows a collection of triggers from non-stationary noise here, and a collection of triggers from simulated CBC signals here. On the x-axis, you have the SNR. On the y-axis, you have this reduced chi-square statistic. And you can see that these two values together allow you to separate the population of triggers nicely. And for example, triggers from non-stationary noise, when they have a very large SNR, they also have a very large value of the reduced chi-square, which is not the case for CBC signals. So then we can invent some other quantity, which we can call, for example, a reweighted SNR, which downranks essentially the triggers from non-stationary noise, which is a function of the SNR and this chi-square value. And these dashed lines here, they are lines of constant reweighted SNR. So you can see that it kind of follows the separation between these two distributions. Okay, very nice. So it looks like we are done, and we can sort of design a little algorithm that should be able to give us some detections. So you take a data segment, you choose a template, calculate the SNR. Is the SNR above threshold? Yes. Then you calculate the signal-based discriminators. You register a trigger with some information. So the SNR, the signal-based discriminators, the time of the merger, the index of the template that generated this, and then you repeat. You repeat for all templates, for 1 million templates, and repeat for 1 million of data segments. So as you can imagine, this is not a trivial operation. You will never do this on your computer. You will need a computer cluster to do this. There are a lot of practical considerations, which in part were covered, I think, by Canton. Well, you need a PST estimate, which I assumed you have. You don't. You need to estimate it from the data, for example, using the Welch periodogram method. but that's fine. You can do that, and I think Canton showed you how to do it in a robust way. You will need to do this over and over because the data is non-stationary, so the PSD will change over time. So you will have to do this over and over. You need to be careful with numerical overflows and underflows because the data from the detectors takes values that are 10 to the minus 20 or less. So if you square it, you're going to have problems in single precision, for example. So you need to be careful with this. I think Canton told you about how difficult it is to actually do a discrete fast Fourier transform. So you need to remember all those things and take into account the fact that at the boundaries, you're going to have some complicated effects, which you need to deal with. And like I have already said, this is going to require a lot of operations. So you need to plan the way that your software is going to do this calculation in a careful way. And you're going to need to parallelize these calculations because they are very independent. So you can distribute them over many computers. You need to be good at coding in some sense. You need to avoid unnecessary operations as much as possible. And you can use technologies like GPUs and TPUs also, if you have them. Okay, now we have to do another thing, which is combining data from different detectors. For example, here you have data from only the LIGO-Hanford detector. You calculate the SNR, you find a peak above your threshold, nice, you have a trigger. And this can already be a candidate that goes into your catalog of CBC triggers. If you have data from 2 detectors at the same time or 3, you can do the same process in the other detectors. And in this case, you have a trigger also in the Livingstone detector. So you have actually a coincident candidate here, which gives you more information. And in Virgo, in this case, we don't have a trigger with this choice of the threshold. Okay. So in practice, what do we do to combine data? There are roughly 3 main methods. You can combine the data between the detectors in an incoherent way, which basically means you take the absolute values of the SNRs in all detectors and you sum them in quadrature to produce a network SNR, which is an expression like this. But you lose the information about the relative phases in the different detectors, which is important. On the other hand, you can do a fully coherent method. So basically, what this means is that you go back to all the derivation that I went through, but you always consider data from all detectors at the same time. So when you write your likelihood function, you can do it for multiple detectors without problems. And then you can define immediately the network SNR in a coherent way, which does have some advantages in terms of statistics, which I probably don't have time to talk about. But it's a bit more complicated because it means that the sky location and the distance are no longer degenerate. And this makes the computation more complicated. What we actually do nowadays is a sort of semi-coherent method where we do this thing first, and then we recover the information that we have previously discarded in doing this incoherent combination. And this is done in the following way. So for single detector candidates, we have only information from one detector. So that's basically the end. We cannot do anything else. So we have the matched filter SNR, the chi-square test, the information about the template, and we can add some priors to this. For example, if we think that equal mass CBCs are more favored than asymmetric CBCs, we can use this information at this point. We have the detector sensitivity at the time of the trigger and the data quality information from Francesco. And we can use this to our benefit in deciding if we have a detection or not. If we have a multi-detector candidate, then we have also the relative arrival times, arrival phases, and amplitudes at all the detectors. And this is actually a very important information because noise will not respect some constraints on these quantities that are respected by astrophysical signals. And so we can take all of these information, put it into a feature vector lambda, and then again, in the spirit of testing the likelihood ratio, we can write a density for signals, a density for noise, take the ratio, and this is going to be our optimal ranking statistic for candidate events. But this is almost the end, but not quite. This ranking statistic is a quantity that it's difficult to interpret. So we don't know if we have a ranking statistic of 20, is that a signal or is that noise? And we would like to sort of calibrate this quantity in a way that is easier to understand. And we do this in two ways. One is by calculating what we call the false alarm rate. So basically, this quantity answers the following question. How often does detector noise produce a candidate event ranked higher than the event that we are thinking about? To answer this, we need to generate a null distribution of the ranking statistic. And this is one of the most difficult problems in designing gravitational wave searches. We can do this in at least two ways. One is by essentially sliding the data of the two detectors by an unphysical amount and then redoing all of this procedure. And the set of candidates that we get represents only noise with some caveats, which are very tricky. Another way is, for example, we can assume that the triggers that we see only in one detector are always noise. And then this is another way, but of course, this also has caveats. This is, in general, a difficult problem, but we can do it. And then we make a plot like this, where we have the false alarm rate of our candidates on the x-axis and the number on the y-axis. And if we had no gravitational waves, we could predict this distribution to be this straight line here. And then we can compare with the distribution that we actually have from our candidates. And you see that this distribution has a tail. And these are our significant candidates. So the false alarm rates of these candidates are, the inverse false alarm rates are of the order of, what is it, 1,000 years, 100 years. So this means that noise will produce a candidate like this once every 1,000 years. So it's very, very unlikely that noise will produce a candidate like this. So we say that this is a very strong detection. There is another thing we can do, though, which is answering a different question. And I expect this to be very confusing. So maybe I will have a lot of questions about this. We ask now, okay, we have a certain candidate. We don't want to know the rate at which the search will produce a candidate like this. We want to know how probable that this candidate is of astrophysical origin. It may seem that it is the same question at the beginning, but if you think about it, it's really a completely different question. And to do this, we calculate this quantity called P-astro, which is calculated like this. We have a model for the rate density of our signal triggers, and a model for the background candidates, which is basically what I've introduced previously. The nice thing here is that these models naturally include the astrophysical expectation for the rates of the CBC signals. So this is a very powerful way to include our prior about the population if we know it. Of course, if we don't know it, then we have a problem, but we kind of know it at the moment because we have many events. And so we calculate this P-astro quantity, and then this quantity is 0 if we are certain that a candidate is of terrestrial origin, 1 if we are certain that it is of astrophysical origin, and 1/2 if we are not sure. And in practice, we are never exactly at 0, never exactly at 1, but for a very strong candidate, we get essentially arbitrarily close to 1. And here you can see a distribution of a sample of a few strong BBH events. This is the ranking statistic on the x-axis and the number of events, cumulative number of events on the y-axis. And you see this blue curve and this orange curve are the noise model and the signal model here, basically. And so you see that as you move from a low value of the ranking statistic to higher values, you basically flip from the null hypothesis to the signal hypothesis. At some point, you have like a threshold, which is about here. Okay, we're done. So we can go now from our detector data to a catalog of candidate events. And each catalog has a false alarm, each event candidate has a false alarm rate, which which is the rate at which the search produces candidates like that, or more significant. We have the SNR, of course, for matched filtering, and then these p-astro astrophysical probability. And that's the end. We have our catalog, and we can do all the science, as we will see tomorrow. How much time do I have? 5 minutes. Okay. Yeah, I can talk a little bit about another thing which is important, which is measuring the sensitivity of the search. So basically, with the false alarm rate, we now control the probability of making a false detection. So that's now under control. But we still have the detection probability. Remember this plot at the beginning where we moved the detection threshold, and we can change the false alarm probability and the detection probability. So basically now we have this quantity, and we can choose the threshold actually that we want. So we can be very strict, and we can only keep events which are very, very, very unlikely to be noise, or we can be very loose, and we can accept false alarms. Maybe we don't care. This depends exactly on what we want to do with the catalog. We have the freedom to control this operating characteristic, but we need to measure also how sensitive each choice is going to be. So we want to measure what is the probability that we will detect a signal with this particular configuration of the threshold. And this is important, for example, because we want to convince ourselves that the search works. Otherwise, there is not much point. But we also need this to measure, for example, the CBC rate, as we will see tomorrow. So this is actually important for science, not just for debugging. And the main method here is that we take a population of CBC signals, we simulate the signals, we add them into the data, which we call injection. We run the search again on this modified data with injections, and we count which injections we find. And then we divide by the total, and we know our detection efficiency. And here you can see an example. So for each dot here, we have simulated many, many signals, thousands of them, at these particular values of the masses. And we have calculated this VT quantity, which is essentially the amount of universe that we can monitor with our search. And this allows us then to calculate the rate of mergers. Okay, I am probably very close to the limit time, but I wanted to put out some names for these implementations of searches that we use in LIGO, Virgo, and Kager. They do basically, well, they do similar things. They all do matched filtering in different ways, which are different trade-offs between computing cost and accuracy. And they differ quite a lot on how they calculate the false alarm rate, for example. So unfortunately, I don't have the time to go into details, but you can, I will give you links about this. And it's very interesting and important to compare the results of these different analyses, because I can assure you the results are absolutely not identical. And sometimes you learn very interesting things about, not only about the signals, but also about the methods. We can have low latency searches and offline searches. So we can have searches that essentially give you a detection in 10 seconds or less. This is important if you want to do multi-messenger astronomy. You need to point a telescope for looking at the afterglow, for example. So you need to be fast. So we have implementations that can do this. And then we have a sort of more careful analysis later on a time scale of months, which can be a bit more relaxed and a bit more reliable also, which we use to generate the catalogs. We can also have divide these approaches in all sky, all time, or blind and targeted. So all sky and all time means essentially that you are looking for anything. You don't know when a signal will arrive. You don't know from which direction in the sky. You look for everything. And this is typically what goes into the catalog. And so you see like the false alarm rate, you see p-astro. But if you have some information about an event, for example, because you see a gamma ray burst, you can do a targeted search that only looks at a particular direction in the sky and a particular window of time. And this actually gives you not really a false alarm rate, because you don't have a process that is producing false alarms. You have only one possibility. And so you have a false alarm probability or a p-value. And this actually is shown in the tutorials. Okay, thank you, I'm done. And I will just leave you some links in this slide with much more material about this cert.
Thank you very much. So we have questions from people online. The first one is by Mohed Rehan, who would like a bit more details about the bracket notation for the match filtering operator. Slide 8. Yeah.
There's nothing magic about this notation. You could write it in a different way. It's just to mark that we are computing an inner product between these S and H, or H and H, which are not just two numbers, they are two functions, if you want, or two discrete data vectors. So it's just a way to write this operation in a compact way.
Okay. Thank you. So there is another question by Tony Matthew, who want to know about the SNR thresholds and how do they affect how much signal get neglected, how many faults detection do we get, and what is the overall effect on the science?
Yep. You can get a sense by looking at these plots, which I said earlier that are completely false, but they are still useful to understand what's going on. So the effect of the threshold is twofold. So you should probably look at this receiver operating characteristic here. So if you lower the threshold, if you move the threshold towards 0, you increase the risk of making a false alarm. So you increase the risk of producing detection when there is no signal in the data. The exact way with which this happens depends on this distribution here, which is a Rayleigh distribution in the case of stationary Gaussian noise. But we said that noise is not stationary Gaussian, so in reality this is a more complicated distribution with a long tail that can go even to thousands, SNR of thousands. In reality, the signal-based discriminators will fix these for the most part. So the Rayleigh distribution here is not actually that wrong. It's a good approximation for what happens in practice. So again, if you push this threshold down, you increase your probability of false alarm, but you also increase your probability of detecting a quiet signal. So the fact is, you have some benefit, but also some drawbacks. So the choice of the threshold is a trade-off between the risk of producing a false alarm and the risk of missing a true alarm. And there is not one recipe for choosing one threshold. There is not one value. The value that you will eventually choose is the result of some considerations that you will have to do very carefully, knowing exactly how all of this works, and also thinking about what kind of signals you want to detect. Are they all always loud, or are they all quiet? Are they sometimes loud, sometimes quiet? All of these considerations are going to affect your decision of this threshold. And also the computing cost, of course, is a consideration, because if you produce a false alert every second, then you will have to do many more operations with all those false alerts, which will lead to nothing. So again, it's a balance between many things. It's a complex choice.
Thank you. There is another question by Ida Khan, who asks, what is the relation between P-Astro and the priors defined in Bayesian inference? Are they directly related?
Good question. So there is certainly at least some relation. Trying to get to the slide. Okay. So the prior that goes into this calculation is actually the population prior. So it's more like the mass distribution for the binaries. And the overall rate of the rate density of the binaries. So basically, how many binaries coalesce per unit volume per unit time. The prior that I think you're thinking about is the prior for parameter estimation of a single signal, well, which is basically well, it can be anything you want, but you can use the population prior as a prior for the parameter estimation, which, well, maybe we'll hear about more tomorrow. But yeah, certainly there is a relation, yes.
Thank you very much. So there is another question by Sampriti Mandal who asks, could you please explain how the template bank works?
How does it work? It doesn't really work. It just sits there and we go through it. So perhaps one thing to explain is how you construct it. So one simple way is you pick a point randomly in the space. You calculate the distance between this point and the previous point and all the other points that you have already in the bank. And if the point is too close, you throw it away. And if it's not too close, you add it to the bank. And you continue. And this will give you a perfectly valid bank. It will be a very slow process, but eventually it will converge and you will get a reasonably good bank. And then I guess for how it works, you just loop over all the points. So you start with one, you calculate the SNR, you store your triggers, you go to the next one, you do the same. And this is explained here. Yeah, you choose a template, calculate the SNR, you compare with the threshold, and repeat. Go to the next template, calculate the SNR. So the algorithm is actually very boring in some sense, and it's very slow.
Thank you. Another question by Arsène Ferrier. Do you need to account for uncertainty in detector responses in filter shape? Slide 8.
Slide 8. Uncertainty in the detector response. Well, certainly there is calibration, which is not perfect, which would affect your H model. So you can basically, you can try to model the calibration uncertainty, which is done, for example, in parameter estimation. You will probably hear about this tomorrow. In searches, actually, it's not so important because the SNR, if you write down the effect of a miscalibration of the detector in the model and you propagate it through the end of this calculation, you will see that it's actually, it's not very important. So we ignore it. But if you had worse calibration, so if you calibrated the detector only to, I don't know, 50%, it would be a problem, yes, but we can do much better than that. So in practice, it's not a problem.
Thanks to our colleague, we can neglect that. Thank you. One last online question. So Faisal Barzi is asking, what is the optimal number of combined detectors to maximize the probability of detecting the signal?
Oh, I wrote a thesis about this. I don't know if I have one answer. So as a very silly question, more is better. But in terms of detection, I would say with 2, you can already do very good. With 3, if they are equally sensitive, you can do significantly better. If you keep adding detectors which are much less sensitive than the ones you already have, they're going to be essentially useless for detection. So for example, using Kagra at the moment for including it in the searches will be absolutely useless. So we don't do it. But one day I really hope Kagra will become as sensitive as the other ones, and then it will be very useful. And it will be very interesting to see. It will also be computationally more expensive. The more detectors you add, will increase the computational cost of the search. So again, there is a trade-off. And probably the optimal solution is going to be I'm just guessing, but around 3 detectors would be my guess of the same sensitivity.
Thank you. Any question? Yes.
Thank you very much. This looks rather mature, very mature, I would say. Is there anything, in your opinion, that needs refinement or work?
Yeah, it's a very good question. Yes, certainly there is always more you could do about data quality problems. So ideally, we will build better detectors that have no data quality problems, and then you could just calculate the SNR and you will be done. But I don't think this will be the case anytime soon. So we will always have to deal with data quality problems. And this will become perhaps even more important when we go to more sensitive detectors. So John will talk about 3G detectors tomorrow. And in 3G detectors, the CBC signals will become so long that they will essentially always overlap with some data quality problems. And so some of the things that we sort of sweep under the carpet at the moment with the current searches may not work anymore and may require further thinking. There is also a completely new technology that is emerging based on matched filtering, and I've briefly hinted at this here. But as I kind of mentioned it en passant, but it's becoming really serious now. And so there are actually now search pipelines which have worked in O4 in production, which are based essentially just on a gigantic neural network where you put the data into and you get the detections out. You have no idea what happens inside, but if you look at the rate of detections and you compare with the other matched filtering searches, they produce very reasonable results. So maybe that's the future, I don't know, but it's certainly a valid approach to be understood better, certainly. So more work will happen there for sure.
Okay, thank you. Any more questions? No? Great, well, thanks again, Tito. Thank you everybody for the great discussion. There is a new one, but coming LIGO India is quite similar to the existing detector. So essentially, that doesn't add much to the probability since we are moving towards third generation detectors. Yes. Maybe having one more detector could help, because if one is down for some reason, the other is up. So you increase the probability of having enough detectors online at the same time. So it's still a little bit better to have one more, especially if it's as good as the other ones. Okay. Thank you very much.